will start to cause your clothes to unravel.
Who did West Dallas play last week? Everyone said they lost that.
Why is Alex not back yet? Wait, so he has to go one?
Yeah.
Oh.
My screen sharing, yeah, good. Oofda. Normally it's cold. I don't know why it's warm in here. You know, it's kind of like when they build a new ship, you gotta take it through its paces. So we're finding that like that alarm goes off, we get sewer smell coming up in the prep room. Oh, the prep room can sometimes just be horribly bad. Horribly. Good morning, Alec. How you doing?
Good.
Good morning, Megan. How you doing?
Good.
Good morning, Ion. Good morning, Chloe. How was your weekend, Ion?
It was good. How's yours?
Mine was fine, thanks. How are you doing, Chloe?
Good.
Good. How you doing, Andrew?
I'm doing good. How are you, Mr. Strauss?
Amazing how your brother so invested in baseball.
Hey, just because one person likes something doesn't mean the whole family doesn't.
But you would think that there would be a little bit of confusion. Everything.
All right, that's the bell. By the way, Keegan, I love your hair. You know, I'm really kind of disappointed because, like, I told my seriously, I'm not making this up. I was like, when I get older, I'm gonna put blue streaks through my hair.
You still could.
And then I got bald. Like, it doesn't really work. It doesn't work. Well, that's what I wanted to do, but then it's just gonna look kind of weird. I don't know, like bald and then blue streak. And then the other problem is, it's like you really can't dye the hair because you cut your hair so short. So I could let it grow long, but then long hair when you're bald doesn't look good. It just doesn't. I would, it's hard to believe, but man, my hair did look like yours. And like Jader's, I just really thick brown hair. But I know it's just hard to imagine. It's sort of, well, I was already going bald in that picture right there. But, time for the pledge. Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Okie dokie. So just a couple of orders of business here. So I updated grades, and I'll update grades again this afternoon. Canvas updates at midnight. So I graded in Canvas, and then I usually let it wait till. Now, like I said, you can take the nuclear quiz retake, but I would like to go over the quiz with you before you take it, and I still haven't posted the answers, or did I? I got to double check if I posted the answers. Good. The other thing that you can do, I did post the answers, good. The other thing is, if you didn't do the wave worksheet, so I just want to just share my screen here. So, like I've said a million times, chemistry is like a sport, you got to practice it. So if you go into quantum mechanics, there's the wave worksheet. Now, if you didn't do it, then you can do the optional one, the redo, okay? Because, like I said, watching me shoot free throws doesn't mean you're going to learn free throws. You've got to get out there and practice shooting. If you want to, you can always go and do that optional worksheet just for fun to get more practice. So it's not, anybody can do it, okay? Your summaries are on your lab are really good. So you can go in there and read. I corrected your grammar. I didn't take off for grammar, but I corrected it just so that you can see better ways to write it. And we'll talk about the summaries more tomorrow. But I did go in and correct your grammar. Our test will be next week, Tuesday. On the wave stuff, okay? And I have to do that to print that off or upload it. Science of it. I want to, well, this has been going on for years, but you guys are probably, maybe you're aware of it, maybe you're not, but if we look at academic success of males versus females, females far outperform boys. Now the question is why? And so there isn't a whole lot of research out there yet because it's really not getting too many people's attention. But if you look at ACT scores, college entrance, this is gonna, about 60% of people going to college are females, 40% are males. And that's across the board for dental school, law school, PhDs, doctors. So the question is, why is there this 20% gap? I forgot what I was supposed to do. I was going to do.
Talking about the wave and wave stuff.
Yeah. Oh, the test objectives. Yep. want to get those test objectives for you. Okay. So like I said, you can do that wave worksheet. It'll give you more practice. What'd you think of that video, Finley? So that video, What is Time? I know it was kind of strange, and I know it's probably hard for you to wrap your mind around it, Sophie, but you really want to think of time as like driving a car. Every single one of us can get in a car and drive it at a different speed, right? So if we all got in a different car and we all drove towards Milwaukee, would we all get to Milwaukee at the same time? No, because if you drive at different speeds, you'll get there at different times. You have to think of time as the same way, that you can drive time at different speeds. So the faster you go, you will get to the future sooner. So if Lars is going really fast and the rest of us are going really slow, Lars will get to the future before the rest of us. It will appear as if Lars is not aging, but for the rest of us, we'll all age. Now, we can't actually do this because you'd have to go near the speed of light, but electrons do and other particles do. So if Lars can get to the future before the rest of us, what that means is what we perceive as the present time is relative. In other words, what Keegan perceives as happening right now is different than what I perceive as what's happening right now. So there's not one reality, there's multiple realities. In other words, there are multiple different present times. There's not the present. There are the presents. And therefore the past, present, and the future, therefore, must also be relative. So what I think happened in the past might actually be the present for somebody else. And what I think would have happened in the future might be someone else's present. And so I know that seems really, really strange, but what that means then, Lola, is that the past, the present, and the future already exist. And so I know, Morgan, you're probably saying that's not, Mr. Strauss, there's no way the future already exists. It does, we just can't see it, okay? We can see into the past. When I look into the past, I know that George Washington crossed the Delaware River. Okay, he had a choice. He didn't have to cross the Delaware, but he did. Just like people in the future, Finley, can look at you and say, Finley came to school today. He had a choice. You didn't have to come to school, right? You didn't have a choice. You had a choice. You didn't have to do it. But people in the future can see what his choice was, okay? So past, present, and future already exist. We just can't look into the future. We're only able to look into the past for whatever reason. We're not sure why. So, but the future's already out there. Do you believe me, Andrew?
Sorta.
No? It's okay. All right, so we're going to go through the periodic table lab unless anybody's got another question about that video. The video? Oh, the lab? Oh, so you can either do the lab or you can watch the video where I go through the steps of the lab. So if you missed the lab or you're a virtual learner, you can either, well, if you're completely virtual, you have to watch the lab. And just out of curiosity, like Alyssa and Andrew, Ayan, Celia, Chloe, Emma, Keith, was it better to have me just videotaping myself? Okay, so I'll do that in the future. I'll just do the lab separately and then videotape it for you guys to watch. Okay? So I'm gonna claim the iPad here. Can you guys hear me at home now?
Yes.
Okay. So it's up to you if you want to upload the lab into Notability or if you want to do it on paper copy, it's up to you. Do you want a paper copy?
Yeah.
Okay. Anybody else? So we're going to go through the reactions, and this will be a good review of balancing reactions from semester 1. Oh, and I should say, like, if any of you back there want to jump on one of those 3 seats, feel free. All right, so all right, although this is from first semester, again, understand that there's going to be some gaps in some people's knowledge, okay? That's just the way it is. So if you already know this, awesome, great. If this is just a little bit of review, great. If you're learning it for the first time, great. But either way, in chemistry, you need to balance reactions, okay? So we're going to start with number 1, and I'm going to help you with them. I'm not going to do it complete. Well, the first one I'm going to do completely, but the rest of them. So you take your magnesium metal and you react it with water. Now, I'm going to write water, Evan, like this, HOH. Why am I going to write it like that instead of H2O? The reason is because it helps you identify the type of reaction, okay? And just a reminder, the reason why I call on people is not to put people on the spot, but it helps me know where your gaps in understanding are, okay? It's not a punishment. It's just a way of giving me feedback, just like the Aspire tests give us teachers feedback as to where we need to improve. So magnesium is all by itself. When you have an element all by itself, it's a single displacement reaction. The magnesium and the hydrogen switch. So you switch the 2 metals or the 2 non-metals, Lily, okay? Now, if you look at the periodic table, you see hydrogen is on the metal side, okay? Now, the correct terminology is I should be saying you switch the 2 cations. Cations have positive charge. Do you know, Lola, how you remember cations have positive charges? You draw your little cat. Meow. And then you ask yourself, are you sure, Mr. Strauss? And then I say, yes, I'm positive. Okay. So cations have positive charge. So that's actually the correct way for a teacher to say it, but it's a lot easier to say, just switch the 2 metals. Okay. So when I switch them, the magnesium will now be with the hydroxide and the hydrogen will be by itself. Can hydrogen be by itself, Abraham? Diatomic. Yep.
It's
So,
part of Brinkelhoff.
and yes, Keith, it is part of Brinkelhoff. So those 7 must be diatomic. Spells out the word Brinkelhoff. So then we have to write our charges. So we switch the symbols RJ. And then we write the charges. Okay, so hydroxide, you're going to look up on Appendix A. Okay. But what about the magnesium, Jader? What's the charge on magnesium? Yep, +2, because it's in the +2 column. A crisscross. Then we want to be cool, so we erase the charges, erase the number ones, and then we balance the whole reaction out, Mike. Doesn't matter where you start. There's one magnesium. But there are 2 oxygens and only 1 oxygen over there. So that means I have to put a 2 out front. Now I have my 2 oxygens. How many hydrogens do I have? 2 there, 2 there, for a total of 4. 2 hydrogens there, and 2 hydrogens there. Okay, so now my reaction is balanced. So I will be grading you on balancing the reactions. Okay, Amanda? Wait, no, you're not Amanda. Maddie. Sorry, Maddie.
Mr. Strauss,
Yep.
this is somewhat unrelated, but I remember last quarter, sometimes I would balance a reaction and then it would be like, I balanced it out, but then it's unbalanced. So I fix it on the other side and then it just is like a big loop. How do you like get out of that?
Okay, so that's a very good question. So what happens if I'm like, okay, so I put a 2 here, and now I'm gonna need a 3 here, and now I need a 4 there, and now I need a 6 there, and now I need a 6 there, and now I need a 4 here, and now I need an 8 here, and now I did a 7 here. And if you find yourself caught in a loop, stop. You did something wrong. Go back, and you'd probably, not probably, it means that you did the products wrong. So if you get stuck in an infinite loop like that, your products are wrong, okay? Like a 3 instead of a 2 like it's supposed to be, okay? So that's a very good question, Chloe. All right, how about, oh, so these 2 did react, okay? You may not have seen it, Maddie, because the bubbles were really tiny, okay? And it took like 5 or 6 minutes, but magnesium and water did react, okay? What about the calcium and water? And I know I'm skipping number 2 right now. We'll come back to it. Did the calcium and water react? Yeah. Was it just a little bit? No, that thing really bubbled a lot, okay? So same type of reaction. You're switching the calcium and the hydrogen. Okay. So I'm going to let you do that one on your own. Okay. So this is going to be your homework tonight, is to go and balance all these reactions. Maybe you just want to do it as I go through it. That's up to you, Lars. A lot of people are able to just balance it as I go through it. Otherwise, it's homework. So when I look at the periodic table, where are magnesium and calcium? They are both metals and they are in the same family. So if they're in the same family, they're going to behave the same way. So if magnesium reacts with water, calcium will react with water. So will strontium, so will barium. And as we found out, calcium is more reactive. So as you go down the periodic table, Karen, things get more and more reactive, okay? I can't get any radium, sorry. But I can get barium. And that's what you do when your dog dies, right? Barium. For the non-metals, it's actually the opposite way. As you go up the periodic table, it becomes more reactive. Okay. So when we look at number 2, the magnesium and the HCl, they did react. What type of reaction is this, Evan? Single displacement, because I have a single element all by itself, right? Think of it, you got a single friend all by themselves, hanging out. They're going to switch with the other positive one. Hydrogen has to be 2, right? And then, Keith, we go to our charge expert, Morgan Mikowski. So what's the charge on magnesium, Morgan? +2. What is the charge on chlorine? All right, so it goes +1, +2, +4, then it counts down, -3.
Oh, -3, -2, -1.
All right, so chlorine is in the -1 column. And then we erase our charges. Your job then is to balance that reaction out, okay? So why didn't we do it with the calcium? Well, if it gave a big reaction with water, what's going to happen when we do it with the acid? It's going to be even bigger, right? So it says do the reaction. I'm sorry, it says write the reaction. It says don't do the reaction. So write the reaction out and you guys can balance that, okay? We're going to skip this question. We'll come back to it at the very end, okay? All right, number 5. We burned the magnesium. Anytime, Lola, oxygen is one of your reactants, it's combustion. So anytime oxygen is a reactant, it's a combustion. This is inorganic. So for inorganic, Jader, we just combine the two. Organic means there's carbon present. Okay, so if there's carbon, it's organic. So you're organic because you're made out of carbon. If you're made out of metal, you're inorganic. So for the inorganic ones, we just combine the two. And then we can do one of two things here. If you want to do the crisscross, you can. But if you're able to reduce, you reduce. Or you can just look at the charges and say, oh, my charges are already balanced. So if they're already balanced, there you go. And then you have to balance that whole reaction out, right? Because it's not balanced yet. Now this was that, it burned really bright and it made that white ash. So the magnesium burned very brightly and then we got that ash and then we put that ash with water. And when we combine those two, you got magnesium hydroxide. So I wouldn't expect you to have known that. That's why we're going through this. But the magnesium oxide, when it reacted with water, made magnesium hydroxide. Well, this is just good review. Let's balance the one up here together. So in order to balance this, I've got two oxygens over here. Again, this is just for review. Can I do this? Can I put a 2 there? No. Okay, you can't balance by using subscripts. You have to balance by using coefficients, right? Now I've got 2 oxygens, but that also means I've got 2 magnesiums, so that I got to put a 2 there. Okay. Any questions on the first page before we move on to the second page? Ready for page 2, Karen? All right. All right. Number 6. Aluminum plus water. The parentheses means that you don't change what's inside of it. Okay. Yes. Okay. Now, here's the thing is if there's a 1 on the outside, parentheses are optional. So if this is just review. So let's say I had sulfuric acid. There's a 1 outside the parentheses. If there's a 1 out there, you don't have to put the parentheses. It's not wrong if you do, but you don't have to. I always do that because it helps you as the student realize you should never change that 4, okay? Because you never change what's inside the parentheses. So that's why I just kind of put parentheses even when they're not needed. All right, so this one, you probably knew this already, Avery, but aluminum and water don't react. Because if they did, we couldn't put soda in aluminum cans. The aluminum would dissolve and that would be bad. But aluminum does react with hydrochloric acid. So again, I suggest that you write these answers down, or at least, you know, if you want to do it on a piece of paper, if you want to do it in Notability, that's totally up to you. So the Cl does not have parentheses, no. You're using parentheses when there's like more than one element. So you've got oxygen and hydrogen. If I had this, I got sulfur and oxygen. So that's when you use parentheses, really. All right, so we're going to do the switcheroo. So then the aluminum is with the chlorine. Hydrogen has to be diatomic. What's the charge on aluminum, Sotera? So aluminum's in the 3+ column, so Sotera said a +3. What about the chlorine? -1. So crisscross your applesauce and then balance that one out. Now here, aluminum is all by its lonesome self. Okay, it showed up at the dance by themselves. So when you show up at a dance by yourself, you're looking to find a partner. Here, aluminum showed up at the dance with chlorine. So now aluminum is looking to switch partners. So it's not a single displacement, it's a double. So switch the two metals. Write the charges. Now, do I bring that subscript over here? No, right? You never bring the subscripts over. You rewrite your charges and then you balance it. Okay. You erase the charges, right, Keith? And then you guys can go ahead and balance that reaction out, okay? So in this class, we study what happens like 99% of the time. We can study some strange branches of chemistry, but we're not going to do that, okay? How many should I have here? 3, right? Because of the charges. But sometimes strange things happen in chemistry, okay? There shouldn't be a minus there, and the sodium got left off. So when we added sodium hydroxide, when we added this, we ended up with a white precipitate. The test tube turned white. Now what's strange was by adding more of it, the test tube turned clear. So when you add it, it turns the test tube white. You add more of it, it turns the test tube clear. So this is where a strange thing in chemistry is happening. The aluminum, instead of taking 3 hydroxides, takes 4 and forms a -1 charge and turns clear. And then the sodium is left by itself, okay? How the heck would you know that? You wouldn't, Lily. That's why I'm showing you it, okay? So this is one of these strange things that happens. So for the first one, what?
Next to the sodium, should I do a
So for the question is, for the first one, should there be a 3 subscript right here? Well, let's put the charges on there and find out. Sodium is a 1+, chlorine is a 1-. So when you would crisscross, it should be 1 and 1. Erase my charges. There we go. All right. Number 8. We're going to do all 3 of them together at the same time. So iron, copper, and zinc plus water. These are transition metals because they're in the middle of the periodic table. And the iron did react, Evan. It was a slow reaction, but the iron did displace. If you own a car, you're probably more familiar with this, but when iron gets wet, it rusts. So when iron reacts with water, Hydroxide to -1, right, RJ? Iron can be more than one charge. Iron can be a +2 or iron can be a +3. So it can be either one, +2 or +3. You can pick either one. So what should we pick, RJ? Pick a charge. RJ says +2, so let's go with +2. 1 goes there, 2 goes there. All right. You didn't have to pick a +2. You can pick a +3. So knock yourself out. Pick whatever charge you want. Then erase the charges when you're done. Erase the number 1 and then balance the reaction. Copper and water, no reaction. Again, you probably already knew this, Lola, because when you throw a penny in a fountain, it doesn't dissolve. You can come back a month later, your penny's still there. Plus, our pipes in our houses and apartments and schools, they're made out of copper. Zinc, no reaction. Right, you just put NR, no reaction. So here, the only one that's no reaction is the copper. The copper didn't react. The other 2 did. So just like the first one, you switch the iron and the hydrogen, pick a charge. Doesn't matter which one you pick either one. Okay. Same thing, the zinc's going to switch with the hydrogen. You'll have to look up the charge of zinc on Appendix A. So for homework tonight, you balance these reactions out. Okay. In fact, there'll be time during the resource period to do it, because we'll stop at 11 o'clock. So you should be able to get these done in class and upload. 10 we didn't have to do, 11 we didn't have to do, 12. So when you mix metals with water, you get bases. Okay, when you mix metals with water, you get bases. We can no longer do number 10 because red phosphorus is used to make meth. And so I can no longer buy it because it's classified differently. So we can't do those reactions anymore. But when a non-metal reacts with water, you get an acid. You don't need to write this reaction down, but I was just going to show this to you. When a volcano erupts, a volcano will put sulfur into the air. That will create sulfuric acid or acid rain. So that's why non-metals in the air make acid rain. So things like sulfur, phosphorus, those things create acid rain. "13, 14, and 15 are a little bit tricky. I'm going to draw a picture of what happened. So hopefully you guys at home drew a picture when you watched the video. But these 2 things do not react. You end up with 2 layers, the dichloromethane on the bottom and the potassium bromide on the top. And the same thing for the other one, you end up with dichloromethane on the bottom and potassium iodide on the top. And then we added chlorine to both of these, okay? That's what happened in number 14, is we added chlorine. For number 14, they did react, okay? So which ones do we switch? So when I look at the periodic table here, Lola, here's iodine, here's chlorine, right? They're both non-metals. So remember, you guys, you always switch the two metals or the two non-metals. So I switch the iodine and the chlorine. Sorry, Abraham, I gave it away. Iodine's diatomic, right? Because it's part of Brinkelhoff. Iodine is kind of a pink. Potassium chloride is kind of a yellowish orange. So what happened is your test tube did this. Whoops. The test tube did this. And then same thing down here. Whoops, I did that wrong. There we go. Bromine's also part of Brinkelhoff. It's diatomic. And that test tube did this. Bromine is brownish orange. Potassium chloride is still yellowish. So the top should have turned yellowish and the bottom should have turned brownish. Maybe it did, maybe it didn't, but that's what it should have happened. So don't forget to balance that whole reaction though. Okay, Finley? You still have to balance the entire reaction. So in other words, given the choice, would potassium rather be with iodine or chlorine? Chlorine, right? The potassium ditched the iodine and hooked up with the chlorine. What about potassium bromide and chlorine? Who would potassium rather be with? Bromine or chlorine? Chlorine. So once again, potassium ditches its date. Elements are kind of like people, they're looking for the bigger, better deal. So given the choice, chlorine is number one. So when potassium's looking for a date, it calls up chlorine first. But what if chlorine is busy? Then who? Iodine or bromine? Who's number two on the list if your first choice for prom is busy? Well, that's where they did the reaction. So as it turns out, they do react. You get iodine, and like I said, iodine is pink. It's the bottom of your test tube turned pink. This is kind of brownish, and the top turned brown. So that means chlorine is number one, bromine is number two, iodine comes in last. Okay, Avery? Time to go to bed last night. That's good. I actually went to bed at 10 too. Woke up at 6. I'm used to it. So there's one more element though in the halogens, right? There's chlorine, there's bromine, there's iodine. Where does astatine come in? Number 4. So basically, Lars, if your top 3 choices are busy, you ask your sister, right? Poor old astatine coming in last place. All right. So I said there was one question I was going to come to at the very end, right? So if we go back to the front page, I said we were going to answer this question later, okay? Oh, I suppose before we answer that question, are there any other questions before I move on? Okay. Give me a thumbs up at home if you're ready to move on. Okay. So we're going to answer on page 1. We're going to answer the question that I just circled there. How do you compare the 2A metals with the 1A metals? So I'm going to show you a little video. I'm going to switch over to my computer to do that. All right, so metals are shiny, right, Karen? Like gold, silver, metals are shiny. Is that shiny? No. This is lithium. But watch what this guy does.
Lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife.
So when they cut out the outer layer, then it's shiny. The other thing that was crazy there, if you saw that, Sophia, he cut it with a knife. Okay, metals are malleable, they're soft. We typically think of metals as really hard. Only the transition metals like, copper and nickel and silver and those things, you can't cut them with a knife. But these other metals, cut them with a knife.
In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire and burns in a light flame.
Did that happen when we did the lab? Did any of our metals catch fire? No. So what about the alkali metals? Are they more reactive or less? The alkalis are the first column, right? These are the alkalis. These are the alkali earths. Okay. Remember, what letters does the alphabet start with, Evan? A. First column is alkali. How many words in alkali earth? 2. Alkali earth are the second column. Okay, that's the way you're going to remember it. So none of our reactions started on fire, so alkali are more reactive. And what's happening to the reactivity as they go from lithium to sodium to potassium? More reactive. So RJ, next on the order, rubidium. You ready to see rubidium, Keith? You pumped?
The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
That's water. So it's just reacting with water. So
About the chemical process of electrolysis.
by the way, remember, you can always go watch Tyler DeWitt. If you find me confusing, I don't take it personally. Go watch Tyler DeWitt. He's good at explaining things. All right, so let's go back to the iPad. Like I said, your homework is to finish balancing these reactions, okay? So that's the only thing you have to do for homework, and then upload it by tomorrow morning at 8:30, but there'll be time during resource today to finish this, so shouldn't take you that long to balance those reactions out. So any questions about the lab or your homework before we move on to quantum mechanics? All right, so we left off with I don't think I showed you the video, did I, of the Rutherford experiment for letter D. Did I show you a little video with an Indian professor? Okay, I didn't think so. All right, so just a reminder, what was the Rutherford experiment? So Rutherford was shooting alpha particles. You're shooting alpha particles at a thin piece of gold. Okay. So why gold? Because you can pound it thinner than paper. And this gold is so thin, Lily, that it's kind of like tissue paper. So imagine what would happen if you fired a bullet at tissue paper. What would happen? Go right through it, right? So that's what Rutherford thought, that he'd shoot these alpha particles, these big, heavy alpha particles, and that they would go right through. Okay? Well, let me show you the video as to what actually happened. Goes this one.
Rutherford's alpha scattering experiment. The credit for the discovery of the nucleus of an atom goes to a British physicist, Lord Ernest Rutherford. Shown here is the diagrammatic view of the famous gold foil experiment conducted by Lord Rutherford. The radioactive source
Let me just, I'll just
rich in
dictate it
alpha
here.
particles was kept in a thick lead block with a narrow opening. The alpha particles were confined to a narrow beam by passing them through a lead sheet with a slit. An extremely thin foil of gold was bombarded with these fast-moving alpha particles. The scattered alpha particles were detected using a rotatable detector, which has a microscope and is screen-coated with zinc sulfide. The whole experimental setup was placed in an evacuated chamber to prevent scattering by the air molecules. These striking particles caused scintillations on the screen.
So he's shooting it through these holes, and then this is what he found. That most of the atoms went, or most of the alpha particles went straight through. So why would those particles go straight through? They would go straight through if the atom was mostly empty space and that there was only a tiny nucleus at the center. So what Rutherford did was he basically discovered the nucleus. See if I can show you one more. No, I think that's good enough. So 90% of the particles went straight through. 10% bounced off. And a very, very, very small number came straight back at you. So again, if you're firing a bullet at tissue paper and 90% of the bullets go through, but a few of them bounce off, and every once in a while the bullet hits the tissue paper and bounces back and hits you, you must be hitting something. And so Rutherford's model of the atom is more what you're used to, in that there's a tiny core called the nucleus. Which question? Which thing? Sophie? A tiny dense positive core. So there must be this nucleus, he called it, at the center. Why? Because when all these alpha particles were shot at it, they went straight through, except for when they hit the nucleus and bounced back. So that's where we kind of get that model of the atom, where that there's this tiny positive core and the electrons go around it. And since 90% went through, the atom is 90% empty space. So the atom is 90% empty. So your head is made of atoms, right, Mike? And the atom is 90% empty space. So I'd be correct in saying that between your ears is 90% empty space. That would be factually correct, right? But we know that there's a problem with his model. And we know this because we already studied nuclear. What's wrong with having two positive charges next to each other? They repel, right? So he knew that there is a problem. And the electrons should be attracted to the nucleus because opposite charges. He knew that was a problem. And the other thing it didn't explain was how metals create spectral lines. So you're like, what the heck's a spectral line? So it's easier if I show you rather than explain it to you. So this is my back. Oh, they're right there in front of Lola. So why don't you guys get up, go over and grab one of those little black boxes. For those of you at home, I'm going to show you a short little video. Right now, everybody's getting a spectroscope. I'm going to show you what a spectroscope looks like. That's a spectroscope. There's an opening on one side, which you look through. And then on the other side, there's a tiny little opening that you look through. So what the classroom is going to do right now is they're going to take their spectroscope, and I don't think I can do this. I know, I don't think it'll work. It might work. Oh, this might work. So I'm gonna turn the lights off, and we're all gonna look at white light. I mean, light from the sun over at those windows in the back. Maybe this will work, maybe it won't. You look through the
Rainbow.
All right. You see a rainbow, right? That is a continuous spectrum. Okay, you see all the colors of the rainbow because the sun emits all types of light. Now what we're going to do is we're going to look at a different source of light, and we're going to get it. This is going to blind you, Keegan. And now, let's see if this works. You don't see a continuous rainbow anymore. You see individual lines. Look at the one I have up in the. See mine? It's not as blended together. you see individual lines. Okay. So what is going on? What's causing this? Actually, just for funsies, point it at the TV screen and see what happens. No rainbow? Small rainbow? How about now? Does it look any different?
It's very low.
Yeah, it's very
Like
dim.
faded.
We are going to play with these things later in the week. So what's causing that? They don't know, right? Again, this is the 1900s. Now, Max Planck, German scientist, I forgot. So that big bright light, that's got mercury in it. That's why it's different. So Max Planck, he was studying this. He had a metal. And he shined light at it. Now we all know light's a wave, right? And he got a few electrons to be ejected. I think I spelled electrons wrong. So if you shine a light on a metal, a few electrons will be removed, okay? Why are they studying this back then? Because they wanted to create electrical currents. Okay. Why do the lights glow? Why do light bulbs glow? There's a metal in there. Okay, and if you get the metal hot enough, the metal glows. Why do metals glow? Okay, we take that for granted because we live in the 21st century. But back then, they're trying to figure out how to make metals glow. Why? So you don't have to use candles. Okay. By the way, do you know how actually they didn't use candles in the 1800s to light up your home? Candles are more like the 1700s. What did they use to light your homes in the late 1800s? Oh, you know, Gavin? Gas lamps, oil lamps. Where was the oil coming from? Not yet. Not yet. It was coming from whales, blubber. That's why we hunted whales, for their oil. We cut those suckers open, blubber, oil would come right out, and we used to light our homes. So quantum mechanics saved the whale. All right, so if you get a few electrons coming off, how can I get more electrons coming off? Add more light. The only problem was more light did not cause more electrons to leave. So more light didn't do anything. So when you get stumped, Karen, it's time to start thinking outside the box. Okay? Almost. So everybody agreed, Jader, that light was a wave. But then Planck said, you know what? Let's just pretend light is not a wave. Let's pretend that light is like a baseball. And instead of waves, you have these baseballs coming at the metal. Like tiny little baseballs. It's not quite a metaphor. No, like just really, really small baseballs, like BBs, flying through the air. I know it's kind of hard to sit there and think like, wait, you're telling me that when I stare at a light, tiny little BBs are going into my eye? Yes, I'm telling you that. Okay. Now, what would happen if what would happen if I increased the frequency at which these BBs came at the metal? And what he found was, if you increased the frequency of these particles of light, not right, these particles of light, more electrons were released. So if you had more particles of light hitting the metal, more electrons would go flying off. So after you've used the word particle of light a million times, Keegan, you're like, there's got to be a better way to say particles of light, particles of light, particles of light. They call them a photon. A photon is a particle of light. And if you're like, come on, Mr. Strauss, there are not little BBs flying through the air into my eye. Yeah, this is not intuitive. This is not something that you would just say, oh yeah, that makes sense. So the energy of these particles is proportional to the frequency. That curvy symbol means proportional to, okay? To turn it into an equation, you add a constant. And in this case, they name the constant after Planck. That's Planck's constant. So H is Planck's constant. You have a question, Lily? No, it's okay. I just want to make sure that, like, I'm not.
Oh, no, you're good.
Okay. So the value of Planck's constant is very tiny. It's 6.626 times 10 to the negative 34th. It is very small. Joules times seconds per one particle. Negative 34th. That number is so small, Planck thought he did something wrong. And he did his experiment over and over and over again, and he kept getting the same number, 6.626 times 10 to the negative 34th. And Planck's constant is one of the magic numbers, Jader. There are a few numbers in science that if you change them just a little bit, electrons, protons, and neutrons will not form atoms. So one of them is the speed of light. Speed of light is 2.99874. You change it to 2.98 instead of 2.99, atoms don't exist. Same thing with Planck's constant. You change this by just a teeny bit, atoms don't exist. Why? Nobody knows. But there are like 8 magic numbers. I think the gravitational constant was one of them. The electromagnetic force is another one of them. But anyhow, that's Planck's constant. You can also put it in kilojoules. In kilojoules, it's 3.99 times 10 to the negative 13th kilojoules times second per 1 mole. So you can put it in moles or you can put it in per 1. Kilojoules times second per mole. And so Planck won, a Nobel Prize for this, and it all came from the fact that he said, let's not think of light as a wave anymore. Let's not do that. Let's think of light as a particle, a little BB flying through the air. And that's where we get the name quantum, because quantum means packet in German. Anything that comes in discrete amounts is quantized. Okay, anything that comes in, discrete amounts means quantum. So for example, Maddie, if you walk into Quick Trip at lunch, you can get a 12-ounce soda, a 16, a 32, and a 2-liter. Can you go buy a 13.2-ounce soda? No. Okay. Sodas only come in 12, 16, 24, 32, 2 liters. All right. Anything that comes in discrete amounts is quantized. So Celia, dress size. Our dress size is quantized. Dress size. Our dress size is quantized. If you go buy a dress, what sizes do they come in? 0, 2, 4, 6, 8, right? So you can't buy a size 1.7 dress, Evan. Okay. What about shoe size, Amanda? Is shoe size quantized? 1, 1.5, 2, 2.5, 3, 3.5. Can you get a size 3.24? No. But your height, is height quantized? No, you can be any height, right? You can be 1.4 meters, 1.42 meters, 1.425 meters, 1.4256 meters. Okay, you can be any height. How about mass? Is your weight quantized? You only come in 150, 160, 170. Nope. You can be any weight you want, right? So if you come in discrete packets, you're quantized. All right. Any questions so far before we do one example problem and then we're done for the day? All right, Gavin, here's our problem. How much energy is in 1 mole of photons with a frequency of 4.2 times 10 to the 16th inverse seconds? So how much energy is in 1 mole of photons with a frequency of 4.2 times 10 to the 16th? So I'm just giving everybody a chance, Chloe, to write the problem down. So we only have 2 equations right now, this one and this one. So first thing you always do, Keith, write down your information. We're trying to find energy. I know my frequency. And then which Planck's constant do I use? So I got two versions of Planck's constant. Use the one that's per mole. So we have our info. That's worth 1 point. Write our equation. That's worth 1 point. Then Alyssa, we plug our numbers in. And don't be afraid of really big answers or really small answers. I put that into my calculator. Seconds cancels with seconds. I have 2 sig figs. Here I've got 3. So I round it to 2 sig figs. So my answer is 17,000 kilojoules per mole. So any questions on that problem? So you're gonna get homework tonight, homework tomorrow night. Oh, sure, I can scroll back in just a second. So your homework tonight is to finish the periodic table lab, okay? Balance all those equations and then upload it. If you didn't do wave worksheet number 1, you can go and do the redo. Again, if you get stuck on this lab, email me. So Alec and Alyssa and Amanda and Andrew, Ayan, Celia, Chloe, Emma, Keith, Maria, Megan, do you guys know what you're supposed to be doing tonight for homework? Alrighty, so the rest of you guys here in class, if you, let's see, wait. Yeah, so you guys can head home for lunch if you want to head home for lunch.
Do we have to do that one or not?
Yes, you still have to balance it out.
This one?
Yep, you have to balance it out.
Mr. Strauss, I have a question.
Yep,
So you said the quiz was next week, Tuesday?
yep.
Well, I have an AP test that day, and it's like probably around the same time.
Oh, yeah, then you'll just have to take it some other time.
All right.
For lunch, yeah, if you're here for resource, you gotta stay here for resource. Yeah. So I'll stay on the line here in case anybody's got a question, otherwise you're free to log off. If you roomies need to go use the bathroom or get up and stretch,